Welcome everyone. My name is Natan Silnitsky, and I'm a backend infrastructure team lead at Wix.com. Now, Wix has huge traffic with more than 500 billion HTTP requests per day and more than 2.5 billion Kafka business events produced every single day. So this talk is about three caching patterns that are used by Wix's 2,200 microservices in order to provide the best experience for our users while also keeping costs down and increasing availability. So a few words about Wix. Wix is a website building platform where you can manage your online presence and also manage your business online. We have more than 200 million registered users, and more than 100 million websites, and growth is continuing all the time. Now, let's see a few issues that are faced by Wix developers. We have to start with Rebecca from Wix Stores, and she's in charge of the store's checkout service. Now, the store checkout service, when it starts up in production, it first requires to get all kinds of app identification data, part of the configuration of the service, from an external service, from Wix App Market Service. And only when it gets this information, it can start up correctly. But what happens if currently there's some issue? Maybe Wix App Market is down, or we have some network issue between these two services for some reason. We still want for Store's checkout service to successfully start up in order to make sure that we keep high availability for our users. Another issue is faced by Alex, also from Wix Stores, and he is in charge of the store's catalog service. And of course, this service utilizes database, and it retrieves and writes information to a store's catalog. Basically, the catalog of all the products that each store and e-commerce provides. Now, lately, Alex noticed that database latency has really increased, and sometimes even requests to fetch information actually fail. So Alex wants to make sure that even though the scale and traffic of Store's catalog grows, that the database doesn't continue to be a bottleneck, and he wants to make sure that there won't be any failures. So as your traffic grows and success happens for your services and microservices, not utilizing a cache will going to increase loading and response times naturally, because you need more CPU power, more time to process because you have bottlenecks in your system. It also increases network costs, especially network traffic going outside of your data center. And it can also perhaps cause database to fail because they cannot handle the increase in load. Now, if you do utilize a cache, then you can actually reduce latency and reduce the needed scale, because responses are already cached. You don't need to compute them again. So you don't need as many Kubernetes pods or instances as with a cache. And it also improves reliability. Even if the database becomes unavailable, for most of the requests that have cache hits, that won't be an issue because they already have a response built into a cache. So I've gathered a few examples from all of the Wix's microservices and put them into categories. So the first category, when and how to use a cache, is when you have high risk or cost of network failure. So if you have an external source of critical configuration data, it means that you probably want to cache it in advance and persist it in order to have a guarantee that you can start up with that configuration, that you can run correctly and have all the configuration you need, even if the external source is unavailable. And also, a lot of the times we want to improve the latency when we retrieve information from our data layer especially when we have high traffic. So in this case, we have our own pattern that we've developed at Wix on top of Amazon's DynamoDB, including an in-memory cache. That means we have zero latency in order to fetch information from our instance memory. And this one also gets updated from DynamoDB using Kafka events through the CDC mechanism. CDC is change data capture, so how we get events from databases. So all this pattern means zero latency access to our cache and much improved latency. Now, the third pattern use case is when you have very high external traffic cases where you have incoming traffic to your system and you want to make sure that incoming request does not impact the amount of CPU and database access and all the other that your microservices and the ecosystem of your microservice requires, because it puts too much load and you can't handle it so much. So in this case, you don't put a cache before your database. You actually put cache proxy before your data center, at the edge of your data center. And this can really improve the situation for your main flows incoming to your microservices. Now, it's also really important to think about when not to employ a cache. So if you have a very young and immature product that you're just starting to check out the waters in production, finding the market for this product, you don't want to add a cache to your architecture for this service because it adds complexity. Maybe you'll have bugs around cache invalidation and you provide stale data for your potential customers. And this is a critical phase for your product development. It's young, you're trying to find the best APIs and the best way to get to your customers, and it's very flexible. So putting a cache there may end up hurting you and being less flexible and bug prone. Okay, so we're going to discuss all the three caching patterns that I mentioned. We're going to see how we can have configuration stored simply in something like S3 in order to make sure that we don't lose critical information in order to healthfully start up. And then we move to our DynamoDB plus Kafka events based in-memory cache on top of the database layer to have better latency and reliability. And finally, we'll talk about the HTTP reverse proxy cache pattern, where you put a cache before your service and it acts like a reverse proxy. So it will avoid getting traffic back to the service. So that's the reverse part here, because it will already have cached HTTP responses. Okay, so let's start with the first pattern. Let's go back and remind ourselves the issue we had with the Wix stores and Rebecca. So for the service to start up correctly, it requires information about the application from an external source, an external microservice, the Wix App Market Service. So what the service employs in order to make sure that it keeps high availability and not fail on startup utilizes a library we developed Wix, very simple implementation. We call it Koboshi or Remote Data Fetcher, which this library is just provided with the code that it requires to fetch some configuration of some static data. In this case, the library will be provided with the code that is required to request app definitions from Wix App Market. Now, what Koboshi will do, it will first check if it is already has a persisted information either on the local disk, or if you're working with Kubernetes and don't utilize like something like stateful sets, then it checks with an object storage service like AWS S3 or Google Cloud Storage and stuff like that. if you work with the Google Cloud. So this way, even if Wix App Market is down, we still have the information found in S3 as the backup. So we don't need to worry about the availability and network with Wix App Market in order for the Wix store service to start up correctly. And of course, even though this is mostly static configuration, Kobashi will try and have a periodic fetching from Wix App Market. So if currently it's unavailable, it will probably be available again in a little while. And then we can get information and repopulate S3. So you may end up with stale data, but if that's the case, maybe this pattern is not right for you. You probably want to have information that it really rarely changes. So summarize this very simple pattern. We have a type of cache which is read-through. Read-through means that the user of the cache doesn't access the source of truth of the data. It only accesses the cache in order to retrieve information. And then this remote data fetcher cache will actually do the job for the service and either fetch it from the service itself or from the backup in S3. And the cache size here has to fit into memory. So here, if you have like a huge data set that you're working with, this pattern is not right for it. And it's best used when you have information that you need to cache, which is probably configuration critical for your service, but it doesn't change very much. It's not for dynamically updating data. Okay, cool. So let's look at a more general purpose kind of pattern that we use a lot at Wix, that we employ with the help of the DynamoDB Amazon database, and including an in-memory cache. So let's go back to the example we had with a database that is starting to really suffer from the increasing traffic. So it has slower interactions. So you may think that you want to maybe split up your database into smaller chunks, maybe sharding, or maybe actually splitting up the domain itself. But a lot of the times, an easier, faster solution is to deploy a cache before it. So in this case, in order to improve latency and not and have better interactions, because remember, the goal here is for the visitor to the Wix site to have the best performance possible and to get a good experience. So we must improve this situation. So how does the service solve it? So each time it writes some update to the database, it also puts it into the in-memory cached key value store. And this works with an LRU fashion. So the least recently used item will be removed, ejected from memory, which usually means that you'll get a high cache hit ratio, right? Because if something hasn't been used for a long time, probably won't be used again soon. Now, whenever it needs to fetch something from the database, instead it will fetch it from the cache. And only if the cache doesn't have this information, it will then go and read it from the relational database. Now, we don't only have in-memory cache, because remember, we have a lot of different instances running in production, right? It's not a single instance. We need to support high traffic. So how will each of these instances get populated in a fast manner? So for that, we don't only put the information into the local cache, we also put it into Amazon DynamoDB. And this way, we have the ability to actually have the information available not only in this specific data center, but in all data centers that Wix operates in. Because with DynamoDB, you get out of the box cross DC data replication and even conflict resolution. So we can make sure that the data is kept eventually consistent all around the world, which is amazing. Now, how will the in-memory caches actually get populated? So DynamoDB has DynamoDB events that we have our own listeners to, and then we produce them into our internal Kafka clusters. So we have a CDC topic. Like I said, CDC is change data capture. It actually has a streaming of all the different update and insert events for DynamoDB. And we can then have a built-in consumer in each of our in-memory cached key value stores. We can have a Kafka consumer that keeps listening to updates for the CDC topic, and then it updates the in-memory LRU cache. So if, for instance, key 1 value has changed from value 1 to value 2, then of course this value will be updated once it is processed by the cache consumer, and it will be found in in-memory cache, and will not have any stale data. We'll have up-to-date data available with zero latency, which is fantastic. Now, what do we do when these service instances start up after a new version is deployed or it's just Kubernetes periodic pod restarts? So now we have a completely clean cache without any information and zero cache hit. So how do we improve this situation? Well, we have our consumer that is reading from the CDC topic, and all we need to do is just read the last, I don't know, like configurable time, like 10 minutes, and repopulate the cache and have the most relevant information, because it's information written in the last few minutes or hours, depending on how you configure it. Which means that we'll not have 0% cache hit ratio. It will actually be a lot higher when we have restarts. Now, you may have a situation where you can keep the entire dataset in memory, and then you can actually utilize the CDC topic and utilize Kafka compact logs. So Kafka topics not necessarily have a policy to clean up messages that are more than 1 week old or something like that. You can actually have a policy where it will only delete stale values for keys, what's called a compact deletion policy, cleanup policy, meaning that you basically have a key value store inside your Kafka topic. Amazing. So if you have a pretty small data set for now for your service to actually cache, then all you need to do is set up your cache with a compact CDC topic. And when you start up, you just load all of the data from the topic. So you have 100% hit ratio. So you have zero latency and 100% hit ratio. Now, if as time goes by and your service is really successful and getting more traffic, no problem. All you need to do is switch from compact mode to delete mode again. So it deletes not stale data, but data that is kept with a longer time period, right? And then you just switch back to take the most recent events. So you have the flexibility here to have, you may not be able to get to 100% cache hit ratio because your dataset is larger than the memory you're willing to pay for in your service. But then you can switch back to the mode that takes the most recent events and still get a very good hit ratio when your store just restarted. So with this flexible configurability, you enjoy all high hit ratio no matter what kind of data you keep. And that's why I meant this is a more general purpose kind of pattern. So most of the time, you would use this sort of cache as a cache aside before your database in order to speed up the most popular queries. But if you don't have any complex querying that you need to do, and you just need to fetch values according to key or the simple key value fetch, then you can actually use this cache as the source of truth database. It will be your key value store with a cache built in, which is really simplifies things. But you need to be careful that you don't need to do any complex querying because with this cache on top, you can only fetch by key and not uh, by some other field that you can index and fetch through with a regular database, but not with this cache. And this is a general purpose thing. You don't need to limit your data size. You configure the amount of in-memory LRU cache you put. You want to put 100 megabytes, you want to put 1 gigabyte, depending on how much memory you're willing to pay for. And it's best to have faster latency when reading from your database or as its own database altogether. Now, you won't really need this kind of pattern for like loading up configuration from some remote service. Well, you can use this pattern, just putting something into S3 and reading it from S3 will probably be better because you don't need really a Kafka consumer that makes this a little bit more latency on startup. You want to optimize startup time. So for that, the previous pattern with static configuration data is best. Okay, so the last pattern for this talk is the HTTP reverse proxy cache pattern, where we have our main service flows for our complete production system, and we want to improve how fast HTTP responses are brought back to the browser, right? Because for our main high throughput flow, we want to have the best experience. So for Wix, the situation is like that for our website rendering. So we have more than 100 million websites that we need to render. And we want to provide the best experience for our customers and for their customers, for the site visitors. We want them to enjoy fast load time. So a few years ago, Wix decided that it will switch to server-side rendering in order to have the best experience on desktop, on mobile, on really slow client devices. So all the computational rendering is done on server side. But still, providing a caching layer here is critical because rendering is very heavy in computation. So we need to make sure that we can avoid that for the more popular websites. So the choice was made to utilize Varnish Cache, which is used as an HTTP reverse proxy. So how it happens is that it is put after DNS resolution and load balancing between the data centers, etc. Then we have the Varnish proxy, and it will check if it has the site rendering response already cached according to the site ID. And if it's not cached, well, then it will get the request forward into the site rendering service. It will actually do the rendering and return the response. Once the site renderer service has the HTML response back, Varnish Cache will cache it for the subsequent calls. And Varnish Cache is open source, so you can use it as well. And of course, something very critical for choosing to use such HTTP reverse proxy caches is to make sure that you have bulletproof way to invalidate the data, because you don't want customers getting into old versions of your site, right? Because we're coming up to Black Friday now, and we've updated our catalog, and we want to make sure that our catalog is cached correctly, right? So how do we make sure at Wix that we invalidate stale caches? So we have our site editor service. So each time that a site version is published, we have a Kafka event where site published purge request event is sent, including the site identification. And then we have a dedicated service, which is in charge of purging stale HTTP responses from Varnish Cache. So it will ask Varnish Cache to purge this site that was published, and it has the site ID. So we utilize HTTP eTag protocol, where for each HTTP request, we also have the site ID, and this way, Varnish will find the correct site and remove it. So now, anytime, the first time that someone will access this site, there will be cache miss, the site new version will be rendered and put into the cache. So it's really important that we make sure that all flows that have some responsibility for what is rendered on specific site versions, all of them have to send out published purge requests. Now let's talk about size limitations here, because we're really talking about a huge scale of traffic, and we said we have more than 100 million websites, right? So with Varnish Cache, you can either go with memory-based cache, and here the size is limited by memory, so it depends on how much you're willing to pay for memory. We also have the possibility to use file-based, disk-based cache. So of course, disks are less expensive than memory, but you can end up with a performance penalty due to disk fragmentation. Now, there is a third option called a massive storage engine that is backed by a file, but it also has a fragmentation-proof algorithm. Now, this type of storage backend is not found on the open source version of Varnish Cache. It's part of Varnish Cache Plus, so it's for paying customers. So to summarize, we have our HTTP reverse proxy cache. It's a read-through pattern, right? A type of cache, because it is in charge of actually accessing the source of truth of the data if there's a cache miss. Now, cache size depends on the storage backend that you choose. With memory, you'll have, of course, bigger limitations. And it is best for improving the latency for external HTTP requests, responses. So, and especially if you have pretty stable, easy to invalidate data. If you have a very complex gathering of all of the information, you aggregate it from a ton of different sources, and each one of them may need to update its data, and you're not sure you will be able to correctly invalidate, then don't use this kind of cache, because it will hurt you more than it will help you in bad experience of stale versions. Okay, so now I have a very simple flowchart for you to be able to use when you want to decide which kind of cache is best for my situation. So you can ask yourself if the data that you're working with is crucial for startup. If the answer is yes, and it's pretty statically updating, then you can just have a pattern where you back up information to S3 or other object cloud storages, where you can easily fetch the information as the primary source or the backup source in order to increase availability for your service, which is very important. When a customer for your service says that it's unavailable, it will go to your competitors. Okay, now if you have a more general case that's not related to actually to startup, and the data does change in a pretty dynamic fashion, then you can go with sort of solution that is backed with DynamoDB and InMemory Cache for zero latency access for the most when you have cache hit. Of course, you could also use Redis clusters or Memcache clusters where you have an extra hop to get to the cache cluster. But for a lot of use cases, that's completely fine. And it's a very popular choice as well. And if you have data that you have a lot of control over, and it's coming from the external part of your system, so you don't want to specifically improve a single database access and latency time, but overall performance for the critical flows of your system, then you can put a reverse proxy cache before your service in order to make sure we have faster responses, faster latencies, higher availability, lower costs, and happy customers. Now, this talk is actually based on a blog post I've written, and you can check it out to get more in-depth details about each of the patterns and how we use them at Wix. And I've also mentioned that we use Kafka, and we actually, for our DynamoDB pattern, we actually use Greyhound on top of Kafka. So Greyhound is our Wix's Java and Scala and JVM high-level SDK for Apache Kafka, and we use it all across our microservices for event-driven architecture to have easier setup of parallel consumption in each of your instances, more resilient consumers with retry policies, resilient producers, saving to disk in case Kafka is down, and a lot of other great features. And it's open source, so you can go ahead and check it out if that sounds interesting to you. And that's all for me. I hope you really enjoyed it. You can find out all of the links I shared and the slides on SlideShare. And you can also check out my website at natansil.com, where you can find previous talks I gave at conferences and other interesting blog posts I have around software engineering and event-driven architecture in general. And you can also follow me on Twitter and LinkedIn, where I put updates on everything we're up to on data streams team, around Kafka, around key value stores, around caches, and of course, updates on software engineering best practices as well. And that's it for me. So if we have any questions, I'll be more than happy to answer them.